right, so here's the 2019 BC exam, question number 2. I've not worked this problem or read it yet, so hopefully I do okay. I just wanted to solve it in real time here. So S is a region bounded by a polar curve, R equals 3 root theta plus sine theta squared. Doesn't look like they're going to introduce any other questions later on, so I'm going to go ahead and let R be F1 in my calculator. So F1, and I don't swap to polar mode. I guess if you really want to, you can, but I've yet to run into a case where I need to. That times the sine of theta squared, x squared. So 3 root x sine x squared, 3 root theta sine theta squared, that's good. I am on 0 to root pi. Let's find the area of S, and they gave us pretty much everything we need to set that up. So the area of a polar region is 1/2 area from A to B, which they tell you we are bounded by 0 and root pi of your r squared, and my function is 3 root theta sine theta squared, all that squared, d theta, so 1/2 A to B of r squared, and then we will throw that in the calculator to get an answer. So back here, it's 1/2 times the antiderivative from 0 to the square root of pi, isn't that what it was? Yeah, of my f1 of x squared. Come on, there we go. So f1 of x squared dx, control enter, force the decimal, and 3.5342. Always go to 3 decimals. What is the average distance from the origin to a point on the polar curve? Okay, so that's just your average value theorem. So that's going to be 1 over b minus a, antiderivative 0 to that. And this time we're doing the distance. By the way, the function r is the distance. So when they say what is the average distance from the origin, that's like saying what is the average value of r. And so it's straight up average value theorem. My r is 3 root theta sine theta squared. Do not accidentally square this thing. We are not doing area. We're just finding the average of the r function. So I'm going to do control divide, 1 over root pi of the antiderivative from 0 to root pi of the function f1 of x, don't square it, dx, control enter, and we get an average value of 1.5799, which you could round to 1.580 or truncate at 1.579. There is a line through the origin with a positive slope m that divides the region S into 2 regions with equal areas, right? But do not evaluate an integral expression, an equation involving one or more integrals whose solution gives the value of m. So we're dividing the region into 2 equal parts with some line m. If the slope is m, okay. That's making it a little bit more difficult because I was about to do 0 to m. So the slope is m. I'm trying to think of a way to do this without having to do like inverse trig to find the... So if I have a line through the origin... Oh, geez, hang on. This little thing I write with sometimes randomly swaps to the other monitor. I have a dual monitor set up. Let's get this oriented again. There we go. All right. So if we have a line that goes through the origin with a slope of m, you know what I'm going to do? I just had an idea. I'm going to move that over here. All right, so I'm going to first find the angle. So I'm going to let theta equal a divide the region. Because if whatever the angle is, that line would be the equation theta equals a. So I'm going to find the value of a. So I'll be 0 to a of 1/2 r squared And that actually needs to give me half of that answer from part A. So that's going to equal 1/2 of 3.534 from part A. The 1/2s would cancel, and I need 0 to A of that function to equal that. That would give me my angle. That would give me the angle, but they didn't give you the angle, they gave you slope. And so if your slope is m, that means I'm rising m and I'm running 1. So my value of A would be the inverse tangent of m, would give you A, right? Because tangent of angle A would equal m over 1. So inverse tangent of m is A, so I'm going to take out that A and I'm going to put the inverse tangent of m. And actually, there we go. We have our equation. We have our equation. You could keep the 1/2 in there. As a matter of fact, I think I will. Because if that region, if that line cuts our region in half, then I need 0 to that line to give me exactly half of the overall area from part A, and I'm good. I'm going to stop there with C. Okay, D. For a positive K, let A of K be the area of the portion of the region S that is inside the circle R equals K cosine theta. Find the limit as K approaches infinity of A of K. How am I on time? Pretty good. All right. So I'm going to draw this really quick. So the region S given to us looks kind of like a teardrop up here. So there's my S. R equals K cosine theta is going to be a circle that goes out like this, where K is going to be the diameter. This is my function R. Okay, we want the area of S that is also inside okay. Interesting. All right, so we're looking at this region right here. We're looking at that region right there. The area of S that is also inside the circle K cosine theta. Find the limit as K approaches infinity of that area. So I think I'm going to find that area. I would have to know the intersection of, so that angle, holy cow, okay, that angle right there where they intersect, I'll call that angle B. And if I want to find that, that would be the intersection of the two curves. So 3 root theta sine theta squared would equal K cosine theta. Obviously can't solve that. The area of a region that is also inside the circle R equals K cosine theta. As K gets to infinity, no, that was a bad idea. As K gets to infinity, this is going to get more and more. Alright, so as K keeps getting larger and larger, this circle is going to keep getting bigger and bigger out this way. And I'm visualizing what's happening here. As K keeps going towards infinity, this circle is going to get huge, huge out this way. And if it keeps blowing up and keeps blowing up, keeps blowing up to an infinite radius or an infinite diameter, the circle is going to be almost flat coming in, and it will approach, it will slowly get more and more. As I keep getting bigger circles, it's going to include more and more of this region in the first quadrant, limiting at the angle pi over 2. So as K goes to infinity, the common area will eventually approach just what's in the first quadrant, and so that's going to be the area from 0 to pi over 2. So this ended up being worthless, that work, I was just thinking. So K approaches infinity of A of t, it's going to be the area inside your R function, sine theta squared d theta from 0 to pi over 2, and it does ask you to find, not set up an integral that would find it. So I'll have to punch that in the calculator. And that's really thinking. I don't like how I came to that solution, just kind of reasoning it out. Well, if it does this, then I guess it'll do that. But I don't know how else you would set this up with more work. This ended up being worthless, so that was unneeded, not needed. And then I'll throw this into the calculator to make this a little bit quicker for me. I'm just going to go bring this up and change the upper limit to pi over 2. Pi over 2. Control enter, and we get 3.324. There we go.